Everyone, thank you so much for being here tonight. My name is Trey Kennedy. I'm an AmeriCorps member serving with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public. We do this through supporting communities and increasing civic engagement. We do this by accomplishing through locally led education efforts and community engagement to address local conservation concerns. Before I introduce tonight's speaker, I have a couple things to go over. Zoom audience, your cameras will be turned off and muted throughout the presentation. If you guys have any questions, please type them in the chat or in the Q&A section. Cara, if you'd like to answer those as we go throughout, if people have any questions, or just save this to the end, you can say that when you introduce yourself. But yeah. Furthermore, Cara, the floor is yours. And if you'd like to give your little spiel here, that is completely up to you. I'm go ahead and gonna turn my camera off, and the floor is yours.
Thank you. Thank you. Thank you for having me this evening. I am Dr. Cara Burberry, PhD, PG, professional geologist in the state of Nebraska. And one of my research directions is the geology of carbon storage, thinking a little bit about what that could do for Nebraska, which is where I'm going to talk to you about tonight. But you're probably wondering what an English girl is doing teaching in Nebraska. I'm a college professor here, and I moved here 15 years ago because this was the job that I got. My previous history has me training in London, and it has me working in the Middle East in the oil industry for a little bit before coming back to teaching. And I have tended to pivot my research direction from oil and gas into the energy transition, which we'll talk about in a little bit, and also knowing that the skills that I gained looking for oil and gas are basically the same skills that you need in the energy transition. So it's been a pivot of a different color fluid and looking to put it back in the ground in terms of carbon dioxide as opposed to pull it out of the ground in oil and gas. But the main concepts of exploration and porosity and permeability are very much the same. So you may hear my dog in the background. She is currently being very quiet and very good, but it is eminently possible that she will not do that for the entire talk. All right, without more ado, I must thank a series of collaborators before I start. Those at UNL was Sam Flegel, Seung-Hee Kim, Latif Lawal, Jesse Chorus, and Matt Jokel, who is actually the state geologist. Sam and Latif were students on a Nebraska Environmental Trust grant, and Sam was awarded a Nebraska Geological Society Yakola Edwards grant to support his research. We spent a little bit of time at the USGS Core Research Facility in Denver in Colorado, and we spent some time in the Conservation and Survey Division Core Repository at UNL, and I have to thank Michelle Vasquez for core access in that particular location. So I think those are my acknowledgements. You see everybody's logos down below. So I've talked a little bit about who I am. We'll go into a little bit of background in carbon capture and storage. We'll talk a little bit, the case study, the main bulk of the story is about Western Nebraska, which is drawn largely from Sam's master's thesis. We'll talk a little bit about some of the issues and the questions that people have about carbon capture and storage, and I'll see if I can preempt some of the questions. But if you have a question, please dump it in the chat and I will see if I can answer it as we go. I'm fairly good at stopping and answering questions in most of my lectures to my freshmen, so we can do that here as well. We'll look forward and then I'll leave a little bit of time for questions at the end, but I'll also leave you my email address. And so if you need or want to ask any more in-depth questions, you're very welcome to contact me. So let's think about what energy transition means. Per S&P Global, the point basically is a shift from fossil-based systems of energy production and to renewable energy sources like wind and solar, as well as lithium-ion batteries. So the focus of energy transition is the idea that we can't just shift immediately away from fossil-based systems. It's not economically feasible to do it just like that. This is driven, the energy transition is done both by climate and economic considerations. And because it's not feasible just to do that, snap my fingers and say, I will no longer use any fossil-based system, then we have to talk about mitigation. And mitigation strategies like CCUS or CCS, which I'll define in a moment, come in. CCS, carbon capture and storage. CCUS, carbon capture, utilization and storage. You'll also hear the phrase carbon sequestration, storing the carbon dioxide underground, which is basically what we're going to be talking about. So the elements of CCS, this image is from the National Energy Transition Laboratory, NETL. Carbon dioxide and capture, direct air capture, for example, or capture off an ethanol plant is not really where I'm going to go today. What I'm going to be doing is talking about storage resources. And what you're seeing in this image is that there are three key possibilities. I hope you can see my cursor. Somebody wave at me or holler at me if you can't. So you can sometimes store carbon dioxide in old coal beds. You can sometimes store carbon dioxide in an old oil reservoir. And the most common one is to store carbon dioxide in a saline formation, a dirty water formation, which is likely to be greater than 10,000 parts per million total dissolved solids. So really kind of gross stuff that you don't want to be drinking. You'll notice also in this image that we're going through something that looks suspiciously like an underground source of drinking water, USDW. Those wells, therefore, have to be cased very, very carefully, secured very carefully, and there are strong regulations about the kind of well that you have to put in order to put CO2 down into the ground. So what's a suitable rock? I gave you three options, and we've mentioned coal, we meant coal beds, we mentioned old oil and gas reservoirs, and those saline formations. Well, those are units that are porous and permeable, that hold and flow fluid, but also they have to be deep enough underground. This image here is a particular core from the research facility in Denver, and you're seeing some reddish rock here, which basically is not porous and impermeable. And so some of this very red rock becomes a kind of seal unit to stop anything escaping. These carbonates from Western Nebraska react with the CO2 and actually trap it underground in mineral formations. What we're looking for is rocks that are cracked rather than terribly solid, so that you've got places to put that carbon dioxide. So, okay, you're thinking, this is all well and good, but carbon dioxide is a gas. How are you going to get it to stay underground? This is, again, a nettle image. And the kind of pressures we're talking about, which was about 3,000 feet underground, that's kind of the magic number, the critical depth here. CO2 is a fluid state of carbon dioxide, supercritical carbon dioxide, the supercritical fluid, as you'll see in the image here where my cursor is showing, held at or above its critical temperature and critical pressure. So what you're seeing is if a balloon is yay big at the surface, as you go further down, the carbon dioxide will become less of a gaseous form and into this supercritical fluid. The drop gets smaller and smaller as you get under higher and higher pressure. But at the reservoir pressures where we try to store CO2 deeper than 3,000 feet, it's basically behaving like a fluid. So let's think about CCS in Nebraska. That's really the focus of what I'm trying to talk about today. And so who are my stakeholders? Really at the moment, because of where we're up to in CCS storage, there's very little, if to no active CCS storage in Nebraska right now, but it's something that's been explored and is a possibility. Energy producers, ethanol plants, and the Nebraska Oil and Gas Conservation Commission is working on rules and regulations for CO2 storage after the bill that will allow CO2 storage in the state to happen was passed. Now, the ethanol board says 2021, but that feels like an awfully long time ago. So that's why my question mark is there. The Nebraska Ethanol Board, this website right here, has, right here, there we go, has a whole page devoted to CCS and notes that many ethanol plants, although possibly not yet in Nebraska, I'm not 100% sure, already capture what's basically very pure carbon dioxide. And so if you're able to capture your carbon dioxide and sequester it or store it, what you get is a lower carbon index on that corn or that soy that you're creating ethanol from. And then, of course, you notice benefits to Nebraskans when that corn is low carbon index, because there are some end users that are really looking for low carbon index materials, low carbon index ethanol. So what do we need to know about our rocks in order to start thinking about storing or sequestering carbon dioxide underground? And this is a picture of Sam at the core repository in Denver. And as you'll see, here is my tape measure, pen, notebook, and a penny for scale. And what Sam is doing is marking out places where we were going to take little plugs of that rock for our colleagues to work on testing porosity and permeability. So there's a couple of things in this process here of looking for rocks to put carbon dioxide in. We log them, which basically means we go, and you see my notebook in the image, and you can see that there are notes there. What I am doing is I am measuring sections of that core, this between 3,000 feet and 3,002 feet deep, the rock looks like this. At 3,002, it starts looking like this. At 3,004, it starts looking like this. And I'm really making notes about this core in very, very fine detail. We chose to take some core plugs home from the repository in Denver. And at that point, what Sam is doing is writing down all our paperwork that we are allowed to take those core plugs home. In Nebraska, the study area we were looking at was basically districts in the NET, Nebraska Environmental Trust divisions, that they were very interested in. The Nebraska Environmental Trust divides Nebraska into a certain number of divisions, or districts, I beg its pardon, and that governed our choice of where we were going to start looking. Also, the availability of core for the units that we were interested in, which I'll show you in a minute, is very much Western Nebraska. There's not at the core repository at any rate. So each little green dot, C142, is a particular core. C143, I'll show you some results from C143. What you're looking at in the image is a geologic map of the western chunk of Nebraska. And these colors, this is the oldest rock. These are the younger rocks. And here is the Platte Valley. And there are things like the Scottsbluff Hills, Scottsbluff and Chimney Rock, and so on and so on and so forth. But there's the North Platte Valley, and there's the South Platte going off into the Julesburg Basin in Denver. This is along the Republican River Valley down in the southern portion. And we were really governed a little bit by the cores that we could access. You can see I'm pointing them out here in my screen. The cores that we could access at the core repository. So what is that geology looking like? We've got rocks that are from about 100 million years old to 65 million years old. That's the Dakota group, that's sandstone, and the Morrison, a little older than that, which is the mudstone unit that usually contains dinosaur bones out west. That's one that gets fossil hunters very, very excited. Getting older, so the base of the Pennsylvanian, I beg its pardon, the base of the Pennsylvanian down in here is about 300 or so million years old. And you'll notice that where there are gray gaps, it means that there is rock that isn't there. Rock of that age doesn't exist in this part of Nebraska. And so we're seeing possible groups of rocks, the Sumner, which is a major seal unit, something that's not porous and not permeable and doesn't allow carbon dioxide to float through. The Lansing in Kansas City, which are all carbonates and mark the rocks that we're really, really interested in. And then the Admire, which is another carbonate sequence, calcium carbonate limestone basically sequence or succession, that could be a storage unit. It's in yellow. It's outlined in red because there are some patches that are very, very tight, which means they're not porous and they're not permeable. And so they might be one of our seal systems. And the way that carbon storage is mandated and governed, you do typically need to have two seal systems, one a primary and a secondary seal above it, just to reduce the chance of any of that carbon dioxide in any case escaping. So what do they look like? I'm telling you about carbonate rocks, and you probably want to know what any of this looks like. This is a glorious fractured carbonate from a particular core. I don't know, I don't have this one logged in my book as or on my slide as to which one it is, but you're seeing natural fractures or natural cracks in the rocks there and there. And this one here, this dark gray wiggly line, which goes up here and up here and up here, is a pressure solution seam or a stylolite where the rock has been pressurized up and down, and part of it is dissolved into the rest of it and been taken out of the sequence. And what it leaves is this slightly impure material like so, that leaves these beautiful wiggly lines. And because that pressure from up and down isn't even in all places, you see these very wiggly lines rather than a perfectly flat surface. So fractured Pennsylvanian carbonates, which is basically what I've showed you before. Again, you've got some other images of these. The fractures are really quite important in these rocks. This is what they generally look like. There's another stylolite. There's my penny for scale. There's another stylolite sitting in there. You can see that a lot of this rock doesn't have a great deal of crack or pore space in it, but there are some that are very, very highly fractured, and that becomes really important because that gives you a permeability system, an ability to flow fluid through the rock that is really quite useful. What you're seeing on the right-hand side is a sequence diagram. So it's basically showing you what the Kansas type possibilities are, the sort of classic, if you will, where you go from sandy shale, mudstone, and coal. So fine-grained rocks with a little bit of sand in it, possibly a big coal, possibly a coal layer where you've had some plant material deposited. This symbol, this blue brick symbol, is the limestone, the carbonate that we're really looking for. And then there's often a shale in the middle. And what that's telling you is that the classic shows a low sea level, a very high sea level, and then a lower sea level again. Now in Nebraska, we see something a little more like this. We don't see that very clear core black shale. What we do see is this reddish mudstone grading into, which means there isn't a clear boundary between the mudstone and the limestone. It sort of merges a little bit into one. And then you get this very clean limestone, which means it's just carbonate and nothing else. And then you go back into the reddish mudstone or siltstone, fine-grained reddish rocks that mark a low sea level. So what these repeated sequences are telling you, because then after this one, you'll go back to here. So this will repeat and stack and stack and stack. And in the Lansing and Kansas City groups, which are the pieces that we're really interested in for carbon storage or as a possibility for carbon storage, you see about 5 of these stacked cycles, one on top of the other. If you've ever been to Schramm Park, to the outcrop at the end of Schramm Park, then what you're seeing is a little tiny piece of one of these, what we call cyclothems. There you are, you have the word right down here, cyclothem. This is the Kansas type. This is a more Nebraska type cyclothem. Under the outcrop in Schramm Park, you see a series of limestones and some shales at the bottom, and the reddish shale at the top, the reddish soil layer at the top, is also a very classic marker across a lot of the state that allows us to correlate or tie particular pieces together. What you're seeing in this other part of the diagram is something that we use to match rock from one area to another area to correlate those rocks across big areas. GR is gamma ray. And so basically what that's pulling out is up here where it's high, there's a large amount of clay in the system. And you can see this very classic shape as it gets suddenly very low clay, getting higher and higher in clay, and there's the clay again. So that's really the depositional setting of these rocks. You've got a rising and falling sea level. You've got these big, thick, clean limestones, which usually don't have a lot of porosity in them, but because of some of the movements that have happened across Nebraska, they become very fractured. As you can see, the porosity of these rocks, if you look at the column down here, this is my porosity column, 5 for porosity, ranges from about 24% porosity down to incredibly low 0.83% porosity. And so the pore size statistics are in this diagram as well, but they've calculated a percentage of gaps in that rock. And those are merely course, these are ID numbers. C143 was a particular core, and S382 is the core that you're seeing in these images over here. There's a plug from S382 at depth 7056. There's a core plug from S382 at depth 7021. And so this comes from the Energy Geosystems Research Group and Latif Lawal, the master's student who was working on this work. And what they basically do is they take a little chip of that rock and they force mercury into it. And the amount of mercury you can force into that rock this is called mercury injection porosimetry. The amount of mercury you can force into that rock is then basically the porosity percent of those rocks. So that's the way that this was measured. That's how that was done. And things are obviously disposed of very carefully per university regulations. That was all information basically from the Lansing in Kansas City. If we move up the succession into the admire, what we're looking at is basically impermeable seals that ensures that the plume, which will spread out a little bit, of the plume of carbon dioxide, which will spread out a little bit through the fracture systems, remains deep underground and stays where you put it. Carbon dioxide is buoyant, it wants to rise, but what we're trying to do here is make sure that we've got seals in place. And this rock, this dolomitic mudstone, that core plug is about the width of my, let's see, about the width of the first joint of my thumb, like this. And what you're seeing is this very fine-grained rock. This was micro CT scanning. This was computer tomography scanning. And the pale white specks are the pore spaces in this particular rock. And so you can see there's the odd big chunk, but they're not connected. And so unconnected pore space is not permeable. That's the difference between the porosity and the permeability. We do have a little bit of pore space in these images, in this rock. This is a slice through it in two different directions. What you're seeing is that there is a little bit of pore space, but the pores are not connected, so you can't flow anything through it. Per EPA regulations, we need a secondary seal kind of above that first one. And so we're working our way, oh, good grief, what did I just do? There we go. We're working our way up the system, up the succession into the Permian or the Sumner group, which is odds on 250 million years old, just to give you a rough sense of what I'm talking about. I'm talking about the Permian, odds on 250 million years old. And this is a very classic gamma ray signature of what's called the Stone Corral Formation. You can see there's my average, there's my dividing line, which is one of the ways we interpret gamma ray logs. Over here, you've got some spikes going to the high gamma end, and then all of a sudden, there's this really thick chunk of low gamma. So very little clay content to almost no clay content, and that can be correlated. And then again, this is showing you in feet below ground surface. Feet BGS is feet below ground surface, 36,000, 37,000, 3700, sorry, 3600, 3700. There's that big chunk in this well, in South Well number 1, which is a different well unit. This is what it looks like, but you can still basically pick the top of that stone corral and the top of that stone corral and say, well, it's higher in South Well than it is in White et al. It must be dipping down in one direction, tilting down in one direction or the other. I don't have a geographic location for these two on this slide. But this big chunk is basically salt. And you can't flow things through salt. It's halite and gypsum. Those are my two minerals in this system, stone corral formation. It's mostly an anhydrite, so a gypsum, which is the same material that's in your drywall. And it is impermeable. You cannot flow carbon dioxide through a salt layer. So that becomes my kind of fail-safe stopgap secondary seal above my primary seal, which allows me to store things beneath it and know that they aren't going to escape if that's what somebody in Nebraska ends up ever trying to do. The next stage in Sam's process was to make a big volumetric model of this chunk of the system. We had hoped to work a little further out here and a little further down here, but what we ended up doing was really focusing on this area because a master's student only has so much time. And what you're seeing is the LKC in this pale blue in this relatively consistent layer. There is north. North is going that way. So these rocks are dipping down very gently or sloping down very gently to the west. And that's pretty typical for rocks in Nebraska. There's our thick unit of the stone corral. This is fairly exaggerated in terms of stretch up this way, but it shows the stone corral, the Admire, and the LKC groups. Other things are kind of lumped in a little bit. We did a little bit of lumping things together just to focus on the units that we really cared about. And there's material, the upper Permian above that. So you'll also notice that this is depth relative to sea level as opposed to feet BGS. That means we're 860, the top of this model is 860 feet above sea level, and this is 2,187 feet below sea level. In terms of converting that to a BGS unit, around here in Nebraska, we're talking about the stone corral being about 3,000 or so feet below ground surface, just to give you a vague sense. So if we're trying to put material, carbon dioxide into the LKC, we are well below that critical level, that magic number of 3,000 feet BGS, where it will start behaving like a fluid and stop behaving like a gas. So we made this basic volumetric model to show roughly what the ground surface looks like. And then Sam made some calculations using CO2 Screen, which is an online tool about how much carbon dioxide can be stored in particular units. And so what you do here is you put an area and a thickness and a porosity and a pressure and a temperature into the system. There's your physical parameters. You give it the standard deviation, 1.7, 6.25 here. Notice my porosity was kind of an average porosity, and this is for the LKC unit, the Lansing, Kansas City unit, LKC, Lansing, Kansas City, which is those deep carbonates that I showed you at the beginning. And my average porosity for those units is about 15.8 based on the calculations that my colleague made in the Energy Geosystems Research Group. We can calculate pressure. We can read off a temperature based on bottom hole temperatures from data around the state. And then we can choose a couple of different modeling techniques, COBRA or IEA, and put in our efficiency factors. Now, what does that mean? That means how much of the area are we going to try and put carbon dioxide into? How much of the thickness is actually useful? So 0.6 of the thickness is actually useful. 0.69 of the porosity is actually useful, as opposed to 100%. So 60, about 70% of the porosity is actually effective, i.e. connected, and we can use it. Whereas in this instance, we got a slightly higher number for our less confident scenario. We got a displacement, we've got a microscopic, we've got some displacement numbers of how we're pushing out what might be already in the system. And this was chosen, most of this was pre-populated in the COBRA system by choosing carbonate, shallow marine, and dolomite as our running material. So we chose this as our basic parameter because that's what fit most of those rocks that I showed you that we're really looking at. A lot of them have been, some of them have been altered to dolomites. So the mineral has changed from a pure calcium carbonate to a calcium magnesium carbonate or a magnesium carbonate. That is the mineral dolomite. And that is a reaction with fluids that pass through the rocks in the process of them turning into rocks and just not being just loose carbonates. So Sam ran a number of these simulations, and one of the things I'm hoping that my incoming student will do is really do some sensitivity testing on what happens if we mess with these systems a little bit. What happens if we mess with these numbers? How much does our P10, our most confident number, change if we are messing with those numbers? How much does our P90 change if we tweak those numbers just a little bit? Still in a reasonable range, but based a little bit more on some additional work that the Energy Systems group did in the engineering campus. So 4 cases of modeling results. We made a small model around a particular area that we're interested in, and we made so you're looking at 2 different programs, the IEA system and the COBRA system. You're looking at a small model and the big one that I showed you of that block model before. And so you see that you get a site model in in the COBRA. You notice the COBRA is usually higher. The small scale model, where we have a little bit more accurate data, gives us really high amounts of carbon dioxide that we could sequester. So this is tons per square mile. So quite a lot of tons per square mile. We're looking at a maximum, but a P90 of about 170,000 tons per square mile of carbon dioxide that you could store. That's a very big range, all the way down to about 18,000 tons per square mile in this model. And this little remark, the 50 megatons, the carbon safe, refers to some work that the DOE has been funding, carbon safe projects. Their goal is to sequester 50 megatons of carbon in a particular situation for 50 years. That's the American standard, is to sequester it for 50, to monitor it for 50 years, and I'll show you some of that in a minute. That plume would be approximately 20 miles wide in the layer that we're looking at. So based on Sam's results and comparing to something that was done by the state geologist here and a PhD student, Valerie Smith, who's now working for a company, Hofstadter and Sleepy Hollow are fields that are slightly further south than our study area. Sleepy Hollow is right on the boundary with Kansas. And the Smith 2020 work estimated much lower amounts of carbon dioxide than we did in our study area. And that's likely because our study area was much, much deeper than the fields mentioned above. Now, remember that carbon dioxide changes size with depth, becomes more pressurized with depth. And so what we're likely to be seeing is that change because the carbon dioxide is basically taking up less space at a greater depth. That's what we think we're seeing and why we think we're getting different numbers than the Smith 2020 work. So what Sam concluded was that the stacked carbonates of the Lansing and Kansas City groups in the study region have estimated storage capacities of 1.8 megatons to 5.3 megatons, and that's per square mile, depending on which model and where you actually start looking. If you start storing things in the Lances Kansas City group, the Admire and the Stone Corral become our really strong primary and secondary seals. And then realistically, if anyone in the state was going to do carbon sequestration work for actual commercial producing or a commercial storage, we would have to drill a test well to fully characterize the lithology in the area. This project was very much an overview of what we could be doing in Nebraska. We chose Western Nebraska. Things are a little deeper, things are the right depth. It's a little more difficult in Eastern Nebraska because fundamentally the rocks dip down to the west, and so the Permian and Pennsylvanian carbonates that we really like the look of stick up at the surface in eastern Nebraska. So the next stage would actually be to drill a well to really characterize exactly what's going on near an ethanol plant that might be wanting to do this kind of work. There's a lot of regulation that goes into drilling a class 6 well, and you can really only get that information by drilling a well. I told you I'd talk about some of the issues and try and preempt one or two of the questions that I sometimes get about this. So if you have, one of the basic things that you need to worry about is you need to worry about existing wells in a region that might possibly allow your carbon dioxide to escape. I see a question in the chat, which is asking, where is the nearest active CCS to eastern Nebraska? I want to say that that is the ADM plant Decatur, Illinois. That's one of the few fields that is reasonably active in CCS at this time. It was one of the good pilot plants, and it's had the odd problem here and there. If you go digging, you can find that it's not a perfect system, but I want to say it's Decatur in Illinois, and that's the ADM plant. So if you've got wells drilled into a region, a study area, like our Western Nebraska study area, if that well penetrates rocks above or into where you want to put carbon dioxide, you need to know that they're cased or recompleted properly. And there were a number of wells that we were really, you see this very high number of wells that we were concerned about in terms of the age of the well and what rocks it penetrated, i.e. going deeper than the units we were looking to store carbon dioxide in, because that might possibly provide a conduit to the surface. So one of the things that would absolutely have to be done in this kind of a project would be to double check, to investigate the state of any existing oil wells in the area. Now, that may sound mildly trivial, but in actual fact, Nebraska was explored quite heavily for oil and gas, particularly in the western area of Nebraska, where this project was looking. And so there are some wells with ages that made us nervous, that may or may not penetrate the units that we were interested in. So that's something that has to be looked into in any kind of project like this. And again, it boils down to will the carbon dioxide stay where you put it? The idea is, yes, it stays where you put it and it just sits there and looks at you. That's a stock phrase, apparently. And if you have a possible conduit to the surface, you need to investigate that conduit. We had hoped to do some further investigation of some of these conduits, but my master's student got a job and graduated and is doing incredibly well. So, seismic activity. This is the one that comes up most of the time. So, what happens if you pump a high pressure fluid, carbon dioxide, down into a unit? Are you going to cause seismic activity? It's the same concern that comes up with fracking and with wastewater injection. And I will contend that when you make a earthquake that you can actually feel on the surface from a process like this, or from a fracture treatment, you've got more problems than humans felt an earthquake, because you've probably blown out your reservoir and your manager will want your head on a plate. So Nebraska's not dreadfully seismically active. You know that we don't feel very many earthquakes. Obviously, there was that swarm in Arnold, Nebraska in 2018, and there are historic earthquakes around the eastern end of the state. This diagram here is showing you the top surface of the Precambrian, so the rocks that are older than 550 million years old. And it's showing you one of the arch systems. And this is again the study area that I showed you before. It's showing you one of the possible fault systems deep in the Precambrian. Now, if one was going to inject carbon dioxide in an area near a fault like that, one would have to do a little more extensive investigation to make sure that that fault doesn't continue. It's in the Precambrian rocks, but does it continue up through the Phanerozoic rocks or not? If it just sits in the Precambrian and looks at you, then if you're high enough above it, so again in that Pennsylvania Permian system, around here, that 300 or 330 million year old rock, then you're probably good. If you're trying to put things right on top of that fault, so you might have noticed there was a basal sandstone in my stratigraphic column, which I showed you earlier. That basal sandstone would be beautiful in porosity and permeability stakes for sequestering material. It's really lovely, but because it's right close to the basement, Precambrian material, where there are some faults, they do tend to just sit there and look at you. We have a tendency not to sequester carbon dioxide in units that are really, really close to these faulted units because of the risk. So those regulations, we're very unlikely ever to be able to drill right to sequester carbon dioxide right on top of the Precambrian rock, because that risk is too high. So the regulations really do try and minimize that risk. You have to do a fair amount of background research, which was out of the scope of this project, but there are certainly people at the CSD working on some of the structures in this area. Ongoing monitoring. One of the big issues in CCS is not only due diligence at the start, i.e. have you made a good geologic model in the way that I tried to show you some of our workflow from earlier? Have you made a good geologic model? Have you made a lousy geologic model? That's where your due diligence comes in, but also the length of time that you are committed to making sure that carbon dioxide stays underground. Now, this is an IEFA compilation from about 2003. So I grant you that it's a little old, but you'll see that the United States has this 50-year bonding period signed into law, where the European Union, Norway, and Australia, for various reasons, have very different systems. And of course, there's always the unexpected. This is a field in Norway called Sleipner, and CO2 is a bit of a tricky beast. Sometimes what you're seeing is that the geologic model had an injection point of CO2 and it went into layers 1 and 2, 3, 4, 5, 6, 6, 7, and 8. And that was designed, the injection point was designed so that the CO2 would buoyantly rise and fill these little sandstone lenses in this system. Unfortunately, we didn't spot layer 9, and CO2 migrated into it, hasn't caused many problems except unexpectedness, as far as I am aware. But this is the Chateau ASA, 20 years of successful storage operations. Please note that this is a 2016 document. So the rapid expansion of layer 9 means that there's a connectivity here that just wasn't anticipated, and that is a surprise. So the ongoing cost of monitoring these fields and the contingency plans, if that particular project starts to fail, my understanding is that it's just unexpected as opposed to majorly problematic. So there are ongoing costs, and I showed you that 50-year bonding cost of monitoring in the US, which was in US law a few years ago. I haven't read an update yet. So it's expensive. But are they higher? Are the costs of working on this kind of project higher than the cost of doing nothing? And again, you get this is slightly old data. This is 2024 data from NOAA, but you see that what you're looking at is a seasonal change in the red. The running average is seasonal change. You're seeing that rise in carbon dioxide. So one of the questions that ultimately does have to be asked is it better or worse to spend money on something like this? Now, I obviously contend that carbon dioxide and sequestration is an important part of the energy transition, but it's not a silver bullet. So CCS is very much here to stay. It's a valuable part of energy transition processes. And this graph is showing you storage planned by 2026, storage existing in 2024, extra storage. This is capture and storage. So full chain means capture and storage. This is extra storage and extra capture projects that are planned out to 2030. And you're going to get 125 megatons of CO2 per year, which is significant, but not perhaps enough to be the silver bullet that solves all our problems. So I think it's here to stay. I think it's a very good thing. And I think that if it ever happens in Nebraska, it will bring really great value to particularly the ethanol industry. Remember, I mentioned that carbon index, and end users really like ethanol with a low carbon index. So that will bring very good value to Nebraska users. With that, I think I will stop, and I will leave you with my email address, and those images are my LinkedIn profile images. So if you're looking for me, you can find me, and I hope I've left enough time for any other questions. Thank you.
Wonderful. Thank you so much, Cara. That was a super interesting presentation. Still just I guess I have a question is if realistically, like how far into the future do you think we could get this incorporated into Nebraska?
I know that some of the ethanol plants have been making noises about drilling stratigraphic test wells. And I know that process, the stratigraphic test well, is a really important part of getting the class 6, the well to sequester carbon dioxide, permitted. I don't know what the update is at the EPA as to where those permits have got to, but I would see it happening. Permitting is difficult. Permitting is difficult because you've got to commit for that length of time.
Mm-hmm.
but I do see it happening 5 years, maybe.
Do you think with Nebraska being um with us relying on a lot of groundwater, do you think that that's contributing to a big issue?
The groundwater system, the High Plains Aquifer, is much higher than a lot of these possible units, and
Hmm.
that always makes people worried, genuinely worried, and reasonably so, that if something happened, our groundwater could be contaminated. Now, what I also know is that any well drilled through that High Plains Aquifer, which these would have to be, have got to be cased, so surrounded by cement is what case means basically, surrounded by cement and surrounded by product that will basically capture any leak from that pipe before it gets into the groundwater. So from my sort of, this is a genuine concern that people have, and it's a question that we should be asking. That's one side of the argument. The other side of the argument is we already know how to protect the aquifer, the High Plains aquifer, pretty well.
Very interesting. I do have another question, but I
Go
will
ahead.
is um which just depending on because you've been around a couple different countries, which
Yes.
country do you think is better with doing this particular practice? United States, UK, I know you mentioned Australia.
So I actually think Norway is one of the leaders.
Okay.
The UK doesn't do a great deal of it. The French do some. Norway, the Sleipner field is a Norwegian field, and that's really kind of the gold standard, although they had a bit of an unexpected layer nine. The Norwegians in the North Sea and other countries that border the North Sea have been trying to do carbon capture and storage for a lot longer than the US has. What's interesting is that there's also a balance between other renewable energy possibilities in Europe, where carbon storage was still is still a much bigger deal for the US because of our reliance on coal.
Hmm.
Now, CCS is one way of cleaning up coal. I don't think you'll ever get to perfectly clean coal, but I think you can get to cleaner coal while we try and transition away from it. Um, and that balance is different in Europe because some of the European countries have already divested from coal completely.
Gotcha. Gotcha. That's all the questions that I had. Did anyone else in the chat have any last minute questions before we decide to close out for tonight? Looks like we do not. Cara, I just want to thank you for taking the time to um, come and do this amazing presentation. I know it's kind of a new concept that is just kind of poking out there, like the conversation we had. But is there any just last comments or things you'd like to leave with the audience before we sign out for tonight?
I think the last thing I'd leave with the audience is kind of a twofold. Don't be afraid of it, but ask your questions.
Mm-hmm. 100% understandable. Okay. Cara, thank you so much. We will definitely be in touch, and this will definitely be up on our YouTube page here. So if anyone else would like to watch it, it will be up. And if Cara, if you need it, it'll be there for you. But that is all that I have. So thank you. I'm going to end the presentation here. So thank you, Cara, and have
Thank
a good
you.
night.
Bye bye.